Today we're going to talk about graphing rational functions. When you're going to graph a rational function, the first thing you need to look at would be domain restrictions, which are any values that will zero out the denominator of the rational function. Usually we find these by factoring. 2. Each domain restriction will either become a vertical asymptote or a removable discontinuity. We should look for the removable discontinuity first. It will create a hole in the graph, and that happens if you, after factoring the denominator, you also factor the numerator and find that you have a common factor that you can cancel. So canceling the common factor creates a simpler function, and we're going to use that simplified function to determine the coordinates of the hole and for any subsequent work we're doing with this rational function. Once you've gotten rid of removable discontinuities, anything that's left as a domain restriction becomes a vertical asymptote. So those are any factors that remain in the denominator, and they are the vertical walls that the graph may not pass through, and they are listed. Like the removable discontinuities are like xy, it's a hole. The vertical asymptotes are x equals some number, and you may have more than one of them. Okay, so let's practice that skill. So first, any domain restrictions. So if I factor this denominator, I get x plus 5. So x cannot be 0 or negative 5. So 0 will either become a vertical asymptote or removable discontinuity, and so will negative 5. Either or, not both. So since my numerator will not cancel either x or x plus 5, then both of these become vertical asymptotes. X equals 0, x equals negative 5. So graphically speaking, we will have a vertical asymptote at x equals 0 and a vertical asymptote somewhere back here at x equals negative 5. Okay. So let's factor this one. This one would be x plus, nope, pardon me, x minus 5, x minus 2. So the domain restrictions, x cannot be 5 or 2, but the x minus 2 will cancel out. So what that means is we have a removable discontinuity, a hole at 2 comma something. The x minus 5 stays, right? This becomes 1 over x minus 5. So the 5 is a vertical asymptote. And the question is, okay, where is the hole? Well, I'm going to plug this 2 back into my simplified function, 1 over 2 minus 5. So that would be negative 1/3. So that's going to look like a vertical asymptote at 5, 2, 3, 4, 5. Vertical asymptote at 5, so a wall here. And a hole at 2, negative 1/3. So there's going to be a hole in the graph. Okay, third one. Without any factoring, I can see that x cannot be 2. My numerator actually is x minus 2, x squared plus 2x plus 4, right? Factoring a cube, and the x minus 2 will cancel. So I don't have any vertical asymptotes. All I have is a removable discontinuity at 2 comma something, and I want to plug that something into my simplified function. Well, my simplified function is x squared plus 2x plus 4. So 4 plus 4 plus 4, 12. So I'm going to have a hole at 212. And by the way, this simplified version is just a parabola. So this graph is going to be a parabola with a hole at 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 212. There will be a hole in the graph. So it's going to look like a parabola with a hole in the graph. Okay, Once we've taken care of domain restrictions, which lead to either removable discontinuity or vertical asymptote, then we consider horizontal or slant asymptote. So a horizontal or slant asymptote is any equation of the form y equals number, that would be for a horizontal asymptote, or y equals mx plus b, that would be a slanted line as an asymptote. And these determine the end behavior of the graph. So a rational function may cross these types of asymptotes because they merely indicate where the ends of the graph are headed. Okay, so here are the rules. If the degree of the numerator is less than the degree of the denominator, then there is a horizontal asymptote at y equals 0. Okay, so that would look like right, horizontal asymptote at y equals 0. If the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is found as the leading coefficient of the numerator over the leading coefficient of the denominator. So it's still going to be a horizontal line. The question is, where will it be? So it could be at 1 or at 2 or at 3 or at -1 or at -2. It's still going to be a horizontal asymptote. If the degree of the numerator is 1 power higher than the degree of the denominator, then there is a slant asymptote, and we'll do long or synthetic division to find the equation of the line that is the slant asymptote. By the way, if you get 0 as a remainder for either your long or synthetic division, then you missed a removable discontinuity, something that canceled. So go back to step 2. Okay. Last possible case, if the degree of the numerator is 2 or more powers higher than the degree of the denominator, then it's possible that you have a quadratic asymptote or a cubic asymptote. And while this work is interesting, most end behavior is either determined by a horizontal or a slant asymptote. Okay, so let's try a few. We would have already done the fact that our domain restrictions, x cannot be 3 or -3. We would have seen that nothing cancels, so we have 2 vertical asymptotes. But our purpose here is to find horizontal asymptotes. And so the degree of the numerator, 2, and the degree of the denominator, 2, are the same. So we have a horizontal asymptote at y equals 4 over 1, right? The leading coefficient of the numerator over the leading coefficient of the denominator. So 4. So we would have 1, 2, 3, 4, a horizontal asymptote at 4. And that means the end of our graph will be sort of approaching that line. In this case, x squared plus 4 doesn't factor. And in fact, x squared plus 4 can never be 0. So we have no domain restrictions, which would mean we have no vertical asymptotes and no removable discontinuities. But the degree of the numerator is 1 and the degree of the denominator is 2. And since the degree of the numerator is less, we have a horizontal asymptote at y equals 0. Okay. So here we have x cannot be 4. It's not going to cancel, so we're going to have a vertical asymptote at 4. The degree of the numerator is 2. The degree of the denominator is 1. And so the degree of the numerator is 1 power higher than the degree of the denominator. So we're going to divide. I could do long division, but since this is x minus 4, I'm going to do synthetic division with 4. 2, -5, 3, so 2, 8, 3, 12, 15. My remainder is 15. I want to see that. If I had seen a 0, it would mean that I should have factored my numerator because I could have canceled my x minus 4. Okay, so my slant asymptote is at y equals, this is x squared, this is x, 2x plus 3. So it's going to be up 2 over 1, up 2 over 1. So This is going to be my slant asymptote. Okay. One of the other things we do is we determine if a graph will cross its horizontal or slant asymptote. And so if it is, we want to know where it's going to cross. So the way we do this is we set the original function equal to its horizontal or slant asymptote. So in this case, the original function for f was 4x squared over x squared minus 9. And we're going to set that equal to its horizontal asymptote at 4. In this case, we're going to have x plus 7 over x squared plus 4. And we're going to set that equal to 0. In this case, we're going to have 2x squared minus 5x plus 3 over x minus 4, and we're going to set that equal to 2x plus 3. Okay, so if we're going to cross our horizontal or slant asymptote, this equation will have a solution. So let's do this one. Let's put this over 1 and do a cross product. So I get 4x squared equals 4x squared minus 36, right? A little cross product here. 4x squareds are going to cancel. I get 0 equals negative 36, which is not true, which means my original f of x graph is not going to cross its horizontal asymptote. In this case, we're going to get x plus 7 equals 0 times that 0. So x equals negative 7. So this graph, the middle graph, is going to cross its horizontal asymptote. It's going to cross it at negative 7. So somewhere, horizontal asymptote here. 1, 2, 3, 4, 5, 6, 7. Somewhere here, my graph is going to cross over that horizontal asymptote. Here we have cross product. 2x squared minus 5x plus 3 equals, let's see, 2x squared plus 3x minus 8x minus 12. So 2x squareds are going to cancel. We get minus 5x plus 3 equals minus 5x minus 12. Add 5x to both sides. I get 3 equals negative 12. Not true. So my third graph is not going to cross its slant asymptote. Okay, those are some skills we'll need for tomorrow.